Before we can really talk too much about the equilibrium, we have to talk about the rate of a chemical reaction. A rate of speed is how fast you're traveling. The rate of a chemical reaction, similarly, is a measure of how fast the reaction proceeds. And one way to measure that is the amount of reactant that changes into product in a particular amount of time. So if the reaction is going quickly, if the rate is high, then a lot of reactant is changing into product, say, in 1 minute. And if the reaction is slow, only a little bit of reactant is changing into product in 1 minute. We have to understand rates because the idea of equilibrium is a situation where the rate of the forward reaction is equal to the rate of the reverse reaction. Reaction rates can be controlled if we understand what affects those rates. And controlling the rates of chemical reactions is actually very important. You refrigerate your meat to slow down the rate of reaction for the reactions that cause the meat to decompose. In manufacturing, where they're making products, they want to control the rates of reactions, maybe speed them up. There might be some they want to slow down. And so it's important to understand what affects rates of reaction. And to look at that, we're going to talk about something called collision theory. Collision theory says that chemical reactions occur through collisions between molecules or atoms. So we're going to look at this simple reaction where one molecule of hydrogen reacts with one molecule of iodine to form 2 molecules of hydrogen iodide. So we have to have a collision. The hydrogen molecule has to literally bump into the iodine molecule in order for there to be a chemical reaction. So they have to collide, and they have to collide with enough energy for the reaction to proceed. The collision energy is related to the particle velocity. So this is a reaction occurring entirely in the gas state. These are gas particles. So we have this particle just zinging through space, and this particle zinging through space. And if they collide, if they hit with enough force, a reaction will occur. If they're going too slowly, if they don't have enough energy, they'll just bounce off of each other. They have to have enough energy. The temperature of a gas is a measure of its average kinetic energy. But some particles have higher kinetic energies and some have lower kinetic energies. So we have these collisions occurring with a distribution of energies. Some of them are high energy, some of them are low energy. High energy collisions are going to lead to a reaction, and low energies are not going to lead to a reaction. Most chemical reactions have what's called an activation energy, a barrier, an energy barrier that has to be gotten over before the reaction can proceed. A lot of times this activation energy is the energy required to break existing bonds in the reactants. If I go back to this, I should have put this on the next slide too. This hydrogen molecule has a bond between the 2 hydrogen atoms. The iodine molecule has a bond between the 2 iodine atoms. In order for the product to be made, those bonds have to be broken. Breaking bonds requires energy. So if these guys run into each other with enough energy to break existing bonds, then the reaction can happen. If they don't run into each other with enough energy, then the reaction will not happen. The factors that influence the rate of a reaction are the same factors that affect the number of high energy collisions that occur per unit time. So if we look at what affects how many high energy collisions we have, we will see that those same things affect the rate of the reaction. Concentration affects the rate of a reaction. If we look, we're going to just keep looking at this same reaction. If we look at a low concentration, a medium concentration, and a high concentration, in which of these situations are there going to be more collisions? You think about people in a room walking around blindfolded. Where are you going to get more collisions? The last one. If there's more people in the same space, if there's a higher concentration of people, there will be more collisions. So a higher concentration means more collisions. The rate of reaction generally increases when the concentration increases. There's a cool video that I found on YouTube. I think what I'll do is I'll show it to you in lab next week when we do the equilibrium worksheets. But it relates this to getting a date, okay? And it talks about running into someone in the hallway and knocking their books on the floor, and then you're picking up each other's books, and in that process you start to become acquainted, and that leads to a date. More collisions, the more people you meet, the more likely it is that you're going to find that special someone, right? This is maybe more like Fresno, and this is maybe more like Wyoming. If there's just very few people, it's hard to meet anyone. The chances of a reaction occurring are going to be smaller than if there's lots of people and you're meeting a lot of people. So this will have a fast initial rate. The low concentration will have a slow initial rate. What happens, though, to the concentration of the reactants as the reaction proceeds? The reactants are reacting to produce the products. There's no resupply of reactants. Reactants that were made into products then are not reactants anymore. So as these molecules run into each other, and maybe they get married, right? So they get married, and more get married, and more get married. Now, the number of single people available is going down because they're being converted into married people. And so then the rate of reaction is going to go down. As a reaction proceeds, the concentration of the reactants goes down, and so the rate changes, and it also goes down. I know I'm mixing my analogies. Temperature also affects the rate of a reaction. Generally, rate of reaction increases with temperature. Again, we're looking at low temperature, intermediate temperature, high temperature. At high temperature, the molecules are moving faster. At low temperatures, they're moving slower. Here, the concentrations are the same. We're just looking at the effect of temperature. If the reactants are moving faster, they're going to run into each other more often, right? Does that make sense? There will be more collisions, and the collisions will be higher in energy, so more of them will be energetic enough to cause reaction. So higher temperature means higher rate of reaction. So, summary of collision theory. Reaction rates increase with increasing concentration, they increase with increasing temperature, and they decrease as the reaction proceeds. They decrease as the reaction proceeds because the reactant concentrations are decreasing. Any questions? So, in a chemical reaction between two gases, you would expect that increasing the pressure of the gases would probably do what? Increase the reaction rate, decrease the reaction rate, or not affect the reaction rate? Increase. Okay, so let's draw a picture. So here we have our cylinder with the movable piston, right? And let me make some gas molecules in here. If I push the piston down, I am squeezing the particles closer together. We don't usually talk about a concentration of gas particles. But if I squeeze them together by increasing the pressure, they have to get closer together. When they're closer together, they're going to run into each other more often. More collisions means faster rate. So increasing the pressure on a gas will increase the reaction rate. Any questions about that? Yes? Would it increase the temperature as well? That's a good question. It depends on how you're controlling your system. A lot of times what will happen is this is in a situation where the temperature is going to be constant because of constant outside temperature, and it's allowed to change its temperature, release the heat. If the temperature also went up, then that would also increase the rate of the reaction. Any other questions?